So the last topic of antiderivatives is rectilinear motion, okay? We're gonna relate this back to how we started the semester talking about distance, velocity, and acceleration, okay? So if you recall, the velocity was the derivative of the position function, okay? So if I have some position function, s of t, and I take the derivative of that, I get the velocity, v of t. So that would imply that the antiderivative of the velocity is the position function. Because if I were to find the antiderivative of this, I should get the position function, because if I take the derivative of the position function, I get the velocity function, okay? So it's just going backwards. Now, the acceleration is the derivative of the velocity, which means the antiderivative of the acceleration is the velocity function. Okay, so that's all that means. You could go backwards. Okay, so if you know the acceleration, you could go backwards and find out the velocity. Now, if you know the velocity, you can go backwards again and know the position. Now, if you know the acceleration, you could just anti-differentiate twice, and it'll give you the position, okay? Now, normally for these types of problems, they give you the initial values. So initial s of 0 and v of 0. So this one is initial position, and this one is initial velocity, okay? So you have an initial position, initial velocity. Remember, we're talking about time here. So t equals 0. We're not going to have any negative values. So let's go ahead and look at a problem. It says a particle is moving with the given data. Find the position of the particle. So they tell you the acceleration is equal to t squared minus 4t plus 6. So that's the initial, that's the acceleration at whatever time. Now let's go ahead and find the velocity. The velocity of the particle, what we have to do is find the antiderivative, because we know the derivative of the velocity is the acceleration. So the antiderivative of the acceleration should be the velocity. As you can see, these are just power rules. Go up one power and divide. You're going to get 1/3 t cubed. We did this example earlier, x squared though, so we already know this one. Now this is a t to the first power. Go up one power, t squared minus 4 divided by 2, which is 2, plus 6t. Think about this as t to the 0. T to the 0 is 1. So if I go up one power, this would be t to the first power, and then divide the coefficient by the 1, you get a 6. Now we have a plus c here. What we need to do is we need to find that c value. They tell us a velocity. The velocity at t is equal to 1 is equal to 20. So it doesn't have to be, when I said the initial conditions, I said s of 0, v of 0. They don't necessarily have to be at 0. Okay, they could be at whatever time. They just need to specify an initial velocity and a position. Okay, so this says take 1, plug it in, set it equal to 20. So 1/3, plugging 1 is very easy. 1 cubed is 1 minus 2 times 1 squared is 1. So this is a 2 plus 6 plus c is equal to 20. So let's see. Putting these two together, you get 4. 4 plus 1/3 is 13 thirds. So this is 13 thirds plus c is equal to 20. So you're going to minus 13 thirds, minus 13 thirds. And I believe you get 47/3. I don't have my calculator near me. So we get a c value of 47/3. After I'm done making this video, I'll go back and check, and if there's anything wrong, I'll say it in an announcement. But now we need the position function. We know the position function. If we take the derivative, we get the velocity. So if we know the velocity, we take the antiderivative, we get the position. So it's undoing the power rules again. So 1/9 t to the, 1/12 t to the 4th. Go up 1 power and then divide. 1/3 divided by 4 is 1/12. Minus 2/3 t cubed plus 3t squared plus 47/3t plus c. So if you notice the antiderivative of a constant, you just tack on the variable to it. This was the power rule. Go up 1, you get a 2. Divide by the power, 6 divided by 2 is 3. Same thing here, the minus sign copies. Go up 1 power, you get a 3. Divide the coefficient by the power, so 2 divided by 3. So this is the antiderivative of this velocity. Now, if I have this piece wrong, the only part that's going to be wrong is this piece. Okay? But the constant still will come out to be the same, even if this piece is wrong. Why? Because s of 0, the other initial condition, is equal to 0. That means plug in 0 everywhere and set the equation equal to 0. Okay? So, 0 to the 4th is 0. 0. 0 to the 3rd is 0. You get 0 from here. 0 to the squared is 0. Plus 47/3 times 0 is 0. Plus c. And we set it equal to 0. So, c was equal to 0 in this case. So, we can get rid of this. So, here is the answer. This is what they are looking for. This is the position function. Okay? Now, again, if I have this number wrong, the only part that's going to be wrong is this piece right here. So, if it's wrong, replace it with the correct number right there, and you'll have the correct answer. Okay? One final example for this section, and it's to talk about graphically what the antiderivative is. Can we get the graph of the antiderivative if we know the graph of the function? Now they show you, if you're looking at my notes, they show you many graphs. Let's see, let me get some colors here to show you what they have. They've got some axes like that, and then in the red they have the function f, and it goes something like this. And then let's see, in black they have an answer choice A that goes something like that. Then in blue, they have B, which goes something like this. And then also in green, they have C, which goes something like this. Now, you're going to look at f, the red. You're going to look at f, and you're going to think to yourself, if I want to find the antiderivative, that means that f is the derivative of my antiderivative. If I know that this is supposed to be a derivative of my antiderivative, I can use the knowledge that I learned in chapter 4 to get information about the graph of the antiderivative based off of this being the derivative, okay? So, I know if f is supposed to be the derivative of the antiderivative, wherever this is equal to 0, I have a minimum or a maximum. So this point right here, I have a minimum or a maximum. So if A, B, or C were to be my antiderivative, it can't be A because I don't have a maximum. This keeps growing like that. But if I look here, I've got a maximum there and I've got a minimum there. So that means either B or C is going to be my answer. But now let's see which one it has to be. We had a test called the first derivative test that allowed us to see whether a particular critical value is a minimum or a maximum. Let's look at f. Again, think about f being the derivative. Since f is negative here, that means over this interval, f is decreasing. So over this interval, f is decreasing, or sorry, the big F, the antiderivative, big F is decreasing because little f is negative. Over here, little f is positive. If that is a derivative, that means my antiderivative is increasing from here to here. So on the left side of my critical value, I'm decreasing. On the right side of my critical value, I'm increasing. By the first derivative test, that means I'm at a minimum. So that would exclude this point because that point would be a maximum. That means my answer has to be B. Okay? If you notice, along this interval right here, I'm decreasing. I hit a horizontal tangent, which would be the 0. And then I'm increasing all along here. If I draw tangents, I'm increasing all the way along there. So that's why the answer is B. And you use the knowledge you have from chapter 4. Act like this is the derivative. What does the derivative say about the original function f?